Welcome to our presentation on Mastering Generalized Linear Models, or GLMs, in Stata. This session is designed to take you from the underlying theory to practical application, specifically for economic research. The concepts and code are compatible with recent Stata versions, including Stata 18, 19, and Stata Now. This approach is crucial when analyzing data that often exhibits nonlinear patterns or specific distributions, a common challenge in economic studies. For instance, you might encounter data like healthcare expenditures, where a standard linear model could predict impossible outcomes, such as negative costs. GLMs provide the necessary flexibility to handle such complexities effectively and derive meaningful insights. Ordinary least squares, or OLS, is a powerful tool, but it often falls short when dealing with real-world economic data. This is primarily because economic data rarely conforms to the idealized bell curve. OLS fundamentally assumes normal errors and constant variance, which are frequently violated. The first major issue is skewness. Much of economic data, like healthcare costs or income, is not normally distributed. It often has a long right tail, meaning a few very high values pull the average up. Second, we have the problem of boundaries. OLS doesn't respect natural limits, predicting impossible outcomes such as negative costs or probabilities greater than 1. Finally, heteroscedasticity is common. This means the error variance is not constant. For instance, spending habits of high-income individuals often vary much more than low-income individuals. If we model wages using OLS, it might predict a negative wage for someone with very low education, which is impossible. These significant drawbacks necessitate a more flexible tool, the Generalized Linear Model framework. Choosing the right GLM starts with the nature of your dependent variable, y. This flowchart provides a simple decision guide. If y is continuous and symmetric, you're in the realm of standard linear regression. You'd use a Gaussian family with an identity link. If y is continuous but skewed and positive, like costs or wages, a gamma or inverse Gaussian family with a log or power link is more appropriate. For binary outcomes, 0 or 1, such as success, failure, or yes-no, the binomial family is the choice, typically paired with a logit or probit link. Finally, for count data, non-negative integers like the number of hospital visits, the Poisson or negative binomial family with a log link is standard. If you are modeling the number of patents a firm produces each year, this is count data. Following the flowchart, you would start by considering a Poisson family with a log link. This flowchart gives a great overview. Now, let's dive a bit deeper into the specifics of these common family and link combinations. Let's look at this table of common choices. The Gaussian family assumes constant variance and uses an identity link, which is just standard linear regression. The binomial family is for binary outcomes. Its variance depends on the mean, u times 1 minus u, and its canonical link is the logit. For count data, the Poisson family assumes the mean equals the variance. Its canonical link is the log link. For skewed, positive data like healthcare costs, the gamma family is very useful. Its variance scales with the mean squared, u squared. While its canonical link is the inverse, in economics, we often prefer a log link. In health economics, we often model cost data. This data is skewed and strictly positive. The gamma family is a good fit for the distribution, but using a log link instead of the canonical inverse link is often preferred because the resulting coefficients can be interpreted as percentage changes, which is very intuitive. Now that we understand the core components and how to choose them, let's review the key assumptions we must satisfy for a GLM to be valid. A generalized linear model, or GLM, is built upon 3 fundamental components. First, we have the random component, which specifies the probability distribution of our dependent variable, y. Unlike OLS, which assumes normality, GLMs allow for flexible distributions, such as normal for continuous data, gamma for skewed positive data, or binomial for binary outcomes. Next is the systematic component, which should be quite familiar. This is our linear predictor, represented as eta equals x beta, meaning a linear combination of our explanatory variables and their respective coefficients. The third and arguably most crucial element is the link function, denoted by g. This function acts as the bridge, connecting the expected value, or mean, of our dependent variable to that linear predictor. It allows us to model non-linear relationships with a linear equation framework. Remember, as the note at the bottom highlights, the inverse link function is essential for mapping our model's predictions back to the original interpretable scale of y. These three components, the chosen distribution, the linear predictor, and the link function, provide a powerful and flexible system. Now, let's explore how to choose the right family and link for different types of data. To ensure the validity of our generalized linear models, we must satisfy several key assumptions. First, independence. Each observation must be independent. If you have clustered data, like students within schools, you should consider alternatives like generalized estimating equations or multi-level GLMs. Second, we need a correct distribution, meaning the chosen family's variance function must accurately describe how the variance of y relates to its mean. A mismatch here leads to incorrect standard errors. Third, a correct link function is vital. It must properly linearize the relationship between your predictors and the mean of y, as a wrong link can lead to biased coefficients. Fourth, linearity implies the relationship is linear on the link scale, not necessarily on the original raw scale of the data. Finally, the assumption of no omitted variables still applies. Failing to include relevant confounding variables will bias your results. As a summary, remember that a wrong family primarily affects standard errors, while a wrong link can bias the coefficients themselves. A crucial aspect of working with generalized linear models is understanding how to interpret the estimated coefficients. Unlike standard OLS, where coefficients directly represent changes in the outcome, in GLMs, the coefficients, or betas, reflect changes in the transformed outcome. The specific economic meaning depends entirely on the link function you've chosen. For an identity link, there's no transformation, so beta represents a straightforward additive unit change in the outcome variable, just like in a linear regression. For example, 1 year of education might increase wages by $5. When using a log link, the coefficient needs to be exponentiated. Here, e to the power of beta signifies a multiplicative effect, or for small values, an approximate percentage change. For instance, if a log link model shows a coefficient of 0.08 for education, it implies that 1 additional year of education is associated with an 8.3% increase in wages. Lastly, with a logit link, which is common in binary outcome models, e to the power of beta is interpreted as an odds ratio. This tells us how the odds of an event occurring change for a 1-unit increase in the predictor. For example, a treatment might increase the odds of recovery by a factor of 1.5. Understanding this nuanced interpretation is absolutely key to communicating your GLM results effectively. To implement generalized linear models in Stata, we use the GLM command. The basic syntax starts with GLM, followed by your dependent variable, or depvar, which represents the outcome you are modeling, such as cost or died. Next, you include your independent variables, typically within brackets, along with optional if and in qualifiers for subsetting your data. The crucial options for GLMs are family name and link name. Family name specifies the probability distribution for your dependent variable, like gamma for skewed continuous data, binomial for binary outcomes, or Poisson for count data. Link name defines the transformation function that connects the mean of your outcome to the linear predictor, with common choices being log, logit, or identity. It's important to remember that if you omit the family and link options, Stata defaults to family Gaussian and link identity, which means the GLM command will behave identically to the standard regress command. Beyond the basic family and link specifications, Stata offers several essential options that help us refine our generalized linear model estimation and reporting. First, the VCE Robust option is crucial. It calculates robust standard errors, which are resilient to violations of the variance assumption and other forms of misspecification. For economic data, where perfect model fit is rare, you should almost always use this. Next, the E-form option is a huge time saver. It tells Stata to report the exponentiated coefficients, e to the power of beta, directly. This gives you easily interpretable odds ratios for logit models or incidence rate ratios for Poisson models, avoiding manual calculation. The Scale x2 option adjusts the scale parameter using the Pearson chi-square statistic. This is particularly recommended for continuous distributions like gamma to correct the standard errors if the underlying variance assumption isn't perfectly met. Finally, no-log is a simple utility command that suppresses the iterative log Stata prints during estimation, keeping your output window much cleaner. With these powerful options at hand, we are well equipped to run robust and interpretable GLM analyses. Now, let's walk through a practical example, starting with data preparation. Before implementing any generalized linear model, thorough data exploration is absolutely essential. We start with the describe command to quickly check variable types. The summarize command with the detail option is a critical step, as it provides crucial statistics like percentiles, minimums, and maximums. This allows us to verify that our data range is compatible with the requirements of our chosen GLM family. For instance, a gamma model requires strictly positive values, as highlighted by the warning on the right. Visually inspecting the distribution with a histogram helps confirm skewness, symmetry, or other characteristics that guide our family choice. Finally, for categorical predictors, using Stata's factor variable notation, like i.variable, simplifies dummy variable creation. Looking at the example output for cost, we see a minimum value of 21.56, which is positive, and a skewness of 1.23. This confirms the data is suitable for a gamma family and reinforces the need for careful data validation. Our goal is to model total healthcare cost based on a patient's age and the type of drug they received. For this, we'll use Stata's built-in cancer dataset. First, we load the data using sysuse cancer clear. Then, for this illustration, we'll create a proxy cost variable by multiplying the study time variable by 1,000. Following this, we immediately visualize our dependent variable using histogram cost. The resulting chart clearly shows a distribution that is heavily right-skewed, with a long tail. This is a classic indicator that a standard ordinary least squares regression would be inappropriate, and a generalized linear model, likely with a gamma family, would be a better choice for analysis. We've explored our data and decided on the appropriate generalized linear model. Here is the complete Stata command to run our analysis. Let's break down each component. We start with GLM cost age I drug, where cost is our dependent variable and age and the categorical drug type are our predictors. The I prefix before drug tells Stata to treat it as a factor variable, automatically creating dummy variables. Next, family gamma is chosen specifically because our cost data is skewed and non-negative, which the gamma distribution is well suited to handle. The link log option models the effects multiplicatively, allowing for an intuitive interpretation of percentage changes. The E-form option is critical for interpretation. It tells Stata to display the exponentiated coefficients, making the output directly interpretable as multiplicative factors or percentage changes. We include VCE robust to ensure our standard errors are robust to potential variance misspecification, which is a common occurrence in economic data. Finally, no log simply suppresses the iteration log, keeping our output clean. First, at the top left, we confirm our model specification. Family is gamma, and the link is log, as intended for our skewed cost data. Now, looking at the main table, because we use the E-form option, the exp-coef column provides exponentiated coefficients, which are direct multiplicative factors. For age, the coefficient is 1.021, meaning each additional year of age is associated with a 2.1% increase in healthcare cost. For the drug variable, compared to the baseline drug, drug 2 is associated with a 25% higher cost, and drug 3 with a 40% higher cost. Moving to the P-Z column, we see that all our predictors, age, Drug 2 and drug 3 are statistically significant at the 5% level, as their p-values are all less than 0.05. Finally, at the top right, model comparison statistics like AIC and BIC are shown. Remember, lower values for these criteria generally indicate a better fitting model, useful when comparing alternative GLM specifications. These coefficients tell us about percentage changes, but to understand the actual predicted cost in dollars, we need to use the margins command, which we'll discuss next. While the percentage changes derived from our log-link model coefficients are informative, stakeholders often require predictions in the original units, such as actual dollars. This is where Stata's margins command becomes invaluable. It automatically handles the retransformation, taking our log-scale coefficients and converting them back to meaningful dollar value predictions. By simply running margins drug, we can calculate the average predicted cost for each drug type, holding other variables at their mean. We then use margins plot to visualize these predictions, complete with their confidence intervals, as shown in the graph. This allows us to see, for example, the clear increasing trend in predicted costs from drug 1 to drug 3, providing a far more concrete and interpretable result than raw coefficients alone. This command makes our complex statistical findings accessible and actionable. A critical diagnostic in generalized linear models is ensuring we've chosen the correct family, meaning the right relationship between the mean and the variance. The modified Park test helps us validate this choice. The process involves a few steps. First, after running our main GLM, we predict the mean of the dependent variable, which we call y hat. Next, we calculate the squared residuals from this initial model. Finally, we run a second GLM, where we regress these squared residuals on our predicted mean, y hat, typically using a gamma family and a log link for this diagnostic regression itself. The key insight comes from the coefficient of y hat in this second regression. If this coefficient is approximately 0, it points towards a Gaussian family, indicating constant variance. A coefficient around 1 suggests a Poisson family, where the variance equals the mean. If the coefficient is around 2, it supports a gamma family, where the variance is proportional to the mean squared. And a coefficient near 3 implies an inverse Gaussian family. For our ongoing healthcare cost scenario, where we've chosen a gamma family, we would expect the coefficient from this diagnostic test to be close to 2, thereby validating our model's family assumption. To summarize our discussion on generalized linear models, here are 4 key best practices. First, always visualize your data first. A simple histogram of your dependent variable is the most important initial step to check for skewness or other features that would make OLS inappropriate. Second, choose wisely. Select the family based on the distribution's shape and the link based on both theoretical grounds and your interpretation needs. Remember that the log link is often preferred in economics for its percentage change interpretation. Third, ensure robustness. Economic data is rarely perfect, so always use VCE robust to get standard errors that are more reliable in the face of minor model misspecification. Finally, focus on clear interpretation. Use the E-form option to get easily interpretable ratios like odds ratios, and use the margins and margins plot commands to translate your results into absolute predictions on the original scale, making them more impactful for your audience.